Alright, let's continue. Let me open the table of content first. Okay. We are in chapter 17. If I remember correctly, we are in homework simulation section here. Okay, let me open that. Okay, the malloc script. Okay. Malloc here. Let me read the readme. Okay. Overview. This program malloc.py allows you to see how a simple memory allocator works. Here are the options that you have at your disposal. Okay, this one. Sheet heap size. Oh, interesting. Size of the heap. Base address of the heap. Okay, size of header. Align allocated units to size. Okay, policy. List order. Okay. Call list of release. Oh, uppercase C. Okay. Number of random ops to generate. I'm assuming ops in here means operation, like the allocation or free operation, maybe something like that. Okay, max alloc size. Oh, okay. Percent of ops that are alloc. Okay, the percentage of operation that are allocation operation. And then op list instead of random list, and instead of random list of ops, the operation. If I remember correctly, plus in here means that the operation is memory allocation, and negative is the, what is it called, the free operation. And we can check this out. Where is it? I think this one, right? So if it is plus, we do some memory allocation. If it is negative, we free the memory. We only have plus size or negative index. Okay. Plus size or negative index. Alright. And then compute unfurl. Okay. One way to use it is to have the program generate some random allocation or free operation, and for you to see if you can figure out what the free list would look like, as well as the success or failure of its operation. Okay. To have the program generate some random allocation or free operation, and for you to see if you can figure out what the free list would look like. Okay. I mean VM free space. Okay. All right. What format is the list? Wait. Oh, uppercase S mean the heap size. Okay. The heap size 100. And what is P? Wait a minute. Maybe something like this. All right. Okay. P is the base address. Okay. Base address, and uppercase H mean the size of the header. Is it in byte? Is the site in byte? Maybe. Okay, and then a alignment, and then list order. Okay, list order, and then the policy is base, I guess. Number of operation to generate. Okay. Alright. In this example, we specify a heap of size 100 bytes, starting at address 1000. We specify an additional 4 bytes. Okay, the measurement is byte here. 4 bytes of header per allocated block, and make sure its allocated space round up to the nearest 4 byte. Right, alignment in here means round up the size, I guess. Okay, we specify that free list be kept order by address increasing. Okay, address sort. Okay, finally, yeah, it is this one. There's L flag here. Finally, we specified a best fit freely searching policy. freely searching policy and asks for 5 random operations to be generated. The result of running these are above. Your job is to figure out what each allocation or free operation returns, as well as the state of the free list after each operation. Okay. Hello Abdul Aziz, welcome. Currently we are reading this book, Operating System 3 Easy Piece, and then we are on chapter 17, checking out the homework simulation script here, the malloc.py. Okay, here we look at the result by using the DESI option. Okay. I want to check what is the free list format here. Okay, return 1000 or 1004. Wait a minute. As said, what is said in this mean? And why is it returning? Oh, free. Okay. Yeah, free. Alright. I am still not sure. Wait, is there an explanation? Okay. Because the initial state of the free list is just one last element, it is easy to guess that the alloc3 request will succeed. Further, it will just return the first chunk of memory and make the remainder into a free list. The pointer return will be just beyond the header. And the allocated space is round up to 4 bytes, leaving the free list with 92 bytes. Starting at Okay, wait a minute. Let me notch this. Heap is 100 bytes. Start address is 1000. The size 4 byte. make sure is allocated space round up to the nearest 4 byte free chunk in size. What is it called again? Alignment, right? Alignment size 4 byte, okay. Free list. Return order, maybe something like that. Address sort, right? Searching policy is best. Okay. Okay. Wait a minute. Return. Unlock 3. Let me try understanding this explanation. It will just return the first chunk of memory and make the remainder into a free list. The remainder into the free list. Is this the remaining size of the heap? Is that it? But then why we take 8? Wait a minute, let me try. Is it something like this, the power? 32, oh. But why is this 80? Yeah, what is unlocked in here means? Not like that, okay. Right, why unlock 5? Need maybe around 12 byte. And unlock 3 needs around 8 byte. Maybe something like that. But why? Wait a minute. Be right back. Masih proses. Okay. Interesting. Okay, because we are not collecting the free list, we now have two elements on it. The first being 8 byte large and holding the just return space, and the second being the 92 bytes chunk. Yeah, I'm kind of curious why unlock 3 return this 1004. Unlock 5, unlock 8. Oh, is it? Oh, okay. Maybe something. Maybe something like this. We unlock 3 plus the header or maybe header, right? 4 plus the allocation value, and then plus the alignment, right? It needs to round up to 4 byte, so that's why this is 8 byte, maybe something like that. The header, and then the, what is it called, the location, it is 9. Oh, and then this one needs to round up again. This is 9 bytes, right? But the thing is that we need to round up to the 4 byte stuff. If we only plus 1, it only 10 byte. It's not really round up to the, what is it called, the modulo 4, maybe something like that. Hold on a minute, be right back. Okay. Byte. Oh. Excuse me. Okay, maybe something like this. Round up to alignment. Okay. Oh, unlock egg. And then if it is unlock egg, four plus egg. So there is no round up alignment here. Okay. Yeah, maybe something like that. Oh, info, okay. presentation, I guess. Okay. So this is the first result of the split. I assume we have heap with the size 100 byte, right? So we split that. Oh, but right, we also need to what is it? No, not that one. Heater, okay, something like this. Okay. Alright. Okay. Size 2. Oh, size is the chunk available here. Okay. Size 1, I guess. Right. We only have one chunk of free space. Maybe I'll let this in here. Size 1. Why the address is okay, because the first address already taken. Okay. Alright. And then size, maybe let's call it remaining 92 bytes, something like this. And then when free tr0, release size 2. That's 1000. Oh, not remaining size. Yeah. And then size 8 bytes. Maybe let's use this. Sorry. Okay, and then 92 bytes. Maybe something like that. PTR1. Okay, we also change this one. The returning address, huh? Oh, wait a minute. Okay, I assume this is 1004 because 1000 until return address. Until 1003 for header, maybe something like this. And then okay, 1012, huh? Interesting. Does that mean okay for let me check 8 until maybe 11 here, but then we also have alignment, right? So what is it called? 117 like this one plus maybe 5 or 4, I guess. Anyway, this one plus this, so maybe around 116 until or maybe 117 until right 16 until 119 for the alignment. So this one become 20, 1020, and this one 80. Maybe something like this because of alignment. If that is the case, it should have alignment too. Oh, maybe what is it called? Maybe 1007 for alignment. maybe something like this. Again, 1004 plus what is it called? 3 negative 1, I guess, because we start at this address, right? So basically 104 until 1006, maybe something like that, and then 1007 for alignment. Okay. Wait a minute. I think something like this. 17, 18, 19. Okay. Maybe okay. And then free PTR1. I'm assuming when we are free the memory allocation, the return is always 0, I guess. So let's just focus on the, what is it called, the free list. Okay, and then from 8, I assume how many bytes again is this? 12 bytes. Okay, right, something like this. Okay. Let me put this here. Guess PTR2 unlock egg for header, and then egg means 12 bytes. Then what is it called? Maybe something like modulo 4. And then return address something like this. Okay. Free list size 2. Okay. Alright. Search 3 element. Size 1. That's 1. element, I guess. Right. And then search to element. Okay. Search 3 element here. Oh, what is the search again? Base. I kind of forgot. Is base fit search until the end? Okay. Search through free list. Oh. Okay. Alright, so we search all the chunk in the list. That's why we search 3 element here, because the previous free list is 3 element. This one, and this one. Okay. Depends on previous free list. Okay, maybe something like that. Oh, that's a lot of information, I guess. Unlock and then free. Unlock. Okay. Oh, there is unlock again. Okay, interesting. Let me try that. Alignment -1. Okay, let me check the code. What? Oh, no alignment. Alright. Okay, if there is no alignment, maybe let me put this here. Oh, not that one. Okay, 100 byte. Start the trace. Header size 0. Oh, interesting. Alignment size also 0. It's not okay. Now let's try this first, I guess. There is no header, so this just 0. Something like this. Unlock 3. No alignment. So this just 3. Return address. I think at the beginning, I guess, until 1002 here, because there is no heater and alignment, it is 0, something like this. This one maybe 3, and 97 byte, maybe something like that. And then 3. Release size 2, because I assume we are not coalescing the free space. This one, size 3 bytes, and then unlock 5. Unlock 5. Okay. So I think 2, 3 bytes, right? Previously, and then until what is it? 7, maybe something like this. And this one is 8. This one is 2, maybe thing like this. Then of course 3 again. Okay, 3. No, not that one. Okay, and then this one is 5. Unlock. Okay. Unlock 8. Okay. I assume we need to split again. Okay. We get the fragmentation here. Okay. 15. Okay. Yeah, this is, what is it called? 1008 plus 8 plus 1, I guess, something like this. 8 negative 1, I mean, because we start from this. 8, 9, 10, 11, and so on. There is that. And then 16, 4, something like that. Okay, and then free. Oh, okay. Gravity R2. Right, the size is 3. The size is 4, I assume. Okay. 16 8 byte, I mean. Okay. All right. Search it. Okay, search one element. Search what is it called? Search 2 element, I guess. This one and this one. And then search 3 element from the previous release, right? And then unlock again TR3. Okay. Search. This is for because it is the best search policy. So we search all the list, all element in the list. Okay. Size. Size 3. Right. Search for element. We take out this one to use for PTR3, and then free again. Size 4. Okay. And then this one. Unlock 2. Unlock 2, Okay. Yeah, let me just use substitute, I guess. Size, maybe size 4, and this one search for element. But the interesting part is that we might take this, right, as big or bigger than the requested size. So maybe something like this. Wait a minute. Okay, maybe something like this until, okay, and then this one becomes something like this. 1 byte. then read this, so continue 7 byte. Okay. 7 byte, maybe this one. We split this one. Okay. 8 until what is it called? 14 maybe, something like that. And then this one is 15 with 1 byte. Let's see how it goes. Okay. Return 1000. Right. This one, the return address. Search one element. Right. The size of the free list. Okay. And this one too. Address 1003 and size 97 byte. Okay. And then we free that. Alright. Having size 2 and then the address. Okay, unlock 5. The return address, something like this. Search 2 element, right? And then the free list 1008 with the size 92. Okay. And let's free this one, size 3. Okay. Not that one. Address 1000, size 3. Address 1000 and 3, size 5. Address 1008, size 92. Okay. PTR2. Alright, we split again, right? PTR2. Where is it? This one. Search 3 element. Alright. Address 1000. Okay. And then splitting up this one. The last chunk. Address 1016 here with the size 84 byte. The result after the split, or the free space after the split, something like that. And then the free PTR2 here, size 4. This one, right? And then the next one is this with size 5. The next one is this one, with size 8 and then this one with size 84. Okay, search for element, right? See, we are searching from the previous list, not from the current list. So this is search for element, and then we are reusing exactly 8 byte of chunk, this one. So yeah, there is no splitting again, at least for PTR3 here. And then free, let me put this on the left, free this, right, and then PTR4, search for element, but because there is no 2 byte chunk, we need to split, and yeah, we split the nearest size, I guess, it is the first chunk. So it becomes something like this. The first chunk reduced, the first free chunk reduced from 3 bytes to 1 byte, right? And then when alloc 7 here, again PTR4, we didn't free this. Oh, right. This would be PTR5. Without freeing the PTR4, we allocate another memory with PTR5 here, 7 byte. The size is still the same, and we search for element again, right? And we split up the third chunk here. Where is it? This one, the nearest, right? So the third chunk from 8 byte become 1 byte here, something like that. Okay. That is quite exercise, I guess. Okay. Wait, did I already read the readme? Okay. And the allocated space is round up to 4 byte, leaving the free list. Okay. 92 bytes starting at 1008. Alright. The pointer return will be just beyond the header. Okay. The next operation is free of PTR0, which is what stores the result of the previous allocation request. As you can expect, this free will succeed, thus returning 0, and the free list now looks a little more complicated, right? Because we are not coalescing Indeed, because we are not coalescing the free list, we now have two elements on it. The first being 8 byte large and holding the just return space, and the second being the 92 bytes chunk. Okay, we can indeed turn on coalescing via the C flag, and the result is something like this. You can see when the free operation takes place, the free list is coalesced as expected. Oh, yeah. If we want to use the coalescing, we can use the dash uppercase C flag. Okay. There are other interesting options to explore. Right, what is it called? The ordering. Oh, the search for free memory, and then the ordering when the memory return the free list, something like that. Okay. This option lets you keep the free list in a particular order, say sorted by address of the free chunk, size of free chunk, either increasing with a plus or decreasing with a negative, right? What is it called? If it is plus, like the size sort plus, it means something like ascending, so the value increase from the top. And if it is mean or negative, like size sort negative here, it will be decreasing, or what is it called? Descending, maybe something like that, from the big value to the lowest value, or simply returning free chunk to the front or back of the free list, right? List ops, this option lets you specify an exact series of requests instead of randomly generated ones. For example, running with the flag this one will allocate the chunk of size 10 byte, the plus header, okay. This one allocate 3 chunk of size 10 byte, and then free the first one, the index 0, this one, and then free the third one, the index 2, this one. So this is index 0, and this is index 1, and this is index 2. So when we are using negative, we are using the index here. Okay, those are the basic. Use the question from the book chapter to explore more or create new and interesting question yourself to better understand how allocator function. Alright. Okay. Maybe I will try out this question on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.